we've been doing, combined gas law stuff. So we're saying that, hey, there's a relationship between volume and temperature for a gas. All of this assumes something. What is this assuming? It's assuming several things, but
This is chapter 11.
this is chapter 11. Yeah, and we're literally doing a quick drive-by. So this is chapter 11, ideas. This assumes that the number of actual molecules of the gas that you have don't change, right? That the volume changes only in response to the pressure and temperature as long as the same number of pieces are present. So what happens if you hold the volume and the temperature or you hold the pressure and the temperature steady, but you double the number of molecules? Is that going to change your volume?
Yes.
Of course it is. You got more stuff. You can't fit the same amount of stuff, or twice the stuff in the same amount of space. So all of this assumes that the number of pieces of gas don't change. Well, what if they do? We need a different equation. So there's a lot of stuff in chapter 11 about Avogadro and molar gas volumes and how the number of pieces are related to these ideas of volume especially, and then pressure and temperature. So we kind of touched on one yesterday, which is that idea of molar gas volume. Gesundheit. And this does come out of some work that Avogadro did. Emilio Avogadro did not come up with the concept of the mole. Avogadro's number was named because he had sort of philosophical contributions that led people to recognize what they were looking at. But we get to this idea of molar gas volumes. So any gas at STP, 1 mole has what volume? Actually, I should change that. Yep. The volume of 1 mole equals 22.4 liters. And that's the first big concept here. So what we're doing is so what 4 things are we specifying right there? It looks simple, but there's a whole bunch of stuff there.
4 things?
Yeah. Name me as many of the things we're specifying as you can. Name me one of them. Tyler. Okay, we're specifying, and I'm going to check these off in orange. The pressure, we're saying it's standard pressure, which is 1 atm or 760 torr. What else are we specifying? The volume. We're specifying that the volume is 22.4 liters. What else are we specifying? The pressure, wait, the what? Temperature, yeah. We're specifying that this is standard temperature, so 273 Kelvin. What else are we specifying? Because these are the 3 things, and you guys did that exactly the way I was hoping you would. That was good job, guys. You didn't even know you were being so clever. Those are the 3 things we've been talking about. But now we're specifying that one new thing. What is it? Ding, 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 ding. Yeah. How many pieces there are? Yeah. Because now we're also saying that these are the conditions for 1 mole of gas. Okay? So what we're about to do, because we're wild and crazy like that, is look at what's called the ideal gas law. And you have probably done this in math. Typically, students come to me and they have done this in whatever academic math track takes their sophomore and junior year, one of those 2 years. Typically, you have done these kind of problems. And the ideal gas law just relates these 4 things. That's all it does. And the ideal gas law looks like this. PV, so far that looks familiar, equals NRT. PV equals nRT. Ideal gas law. Have you seen this in math? Have you rearranged this? Look familiar to anybody? No? Okay, maybe when they changed the math book, maybe that no longer happens. Because I think the old series that they used to use was really good at using equations that actually came from chemistry and physics. Because I used to get students who would say, like, oh, we did problems with that equation. Okay, cool. Okay, so pressure, volume, pressure times volume is equal to nRT. Well, you know what T is. That's temperature in Kelvin. N, you might or might not remember, N is usually a number of something. This is the number of moles. So the one thing we're left wondering about is R. What on earth could R be? Well, it could,
Is it ratio?
but it's not. It's not. It's actually something you've never seen before. Okay. R is something called the ideal gas constant. Do you know what a constant is? Okay, something that doesn't change. What else? What else do you know about the word a constant as we talk about it in math or science?
It's always the same. Oh, sure.
Well, no, yeah, it's something that's always the same. Anything else? That's very much the base idea. When we talk about a number being a constant, it's usually like a factor that relates other things. So the ideal gas constant is this number that never changes, it is constant, that relates the pressure, volume, number of moles, and the temperature of a substance. And the ideal gas constant has got some weird units. Well, let's do this. But this is one of the actual Chapter 11 slides. And if anybody wants them, I will put the Chapter 11 notes up on Classroom. You're not responsible for them. You don't have to do anything with them. But if you want them because you think they might be helpful in college chem, you can have them. I think they desperately need reworked. There's a lot of stuff that I look at it now. I made these when I was first teaching chemistry, and I think I need to change it up. So that ideal gas constant, R, has this value, 0.0820578 liter ATMs over mole kelvins, and we round it to 0.0821. How the heck do you remember that? You don't. I'm of a mind that memorizing things that you can do something else with is a waste of brain cells. Don't waste your brain cells. They're a limited resource. Well, turns out we can calculate the ideal gas constant anytime we want, because all it is, and it took me, I think, 3 years of teaching chemistry to figure this out, that all the ideal gas constant is a statement of mathematical reality. So cool. Watch this. So ATM liters over mole kelvins. So R equals 1 ATM times 22.4 liters over 1 mole times 273.15 degrees Kelvin. Well, that gets you R equals 0.0821 ATM liters over mole Kelvin. Literally, if you multiply those things and divide them, that's the number you get. You don't have to memorize the ideal gas constant. All you have to do is remember that at STP, 1 mole of gas takes up 22.4 liters. But wait!
May I have your attention?
Okay, well, R, the gas constant, what if you're not working in ATMs? What do you have to do if you've got a problem and you're not working with your pressure values in ATMs? You could convert your pressure, but it just so happens that there is a gas constant for every single unit of pressure, because it's just a statement of fact. So what's standard pressure in torr? 760. Well, R is also equal to 760 torr times 22.4 liters over 1 mole times 270, whoops, can't write a 3.15 Kelvin. Go ahead and multiply that out, see what you get. Okay, so done that way, I get 62.3, or yeah, 32473 torr-liter mole kelvins, torr-liter over mole kelvins. Now, what I forgot is that 0.15 does not get used. So what your book gives for the ideal gas constant in torr is 62.4. You can figure out the ideal gas constant with any of the pressure units. All you have to do is take the value for standard pressure in those units and then plug it in. If you can remember the units, you know, pressure times volume over moles times temperature, you got it. It also means that when you're rearranging this equation, if you write down the units for R, you'll be able to see automatically if your algebra is good because your units should cancel. So that's really the 2-minute thing. We're probably honestly going to do a little bit of time with this tomorrow because I do want to walk you through a couple sample problems. It is some, I want to talk a little bit about stoichiometry of gases. So we'll stop there and pick it up tomorrow briefly.